Again, we're getting towards the end. We have 3 more videos to do. And so in this topic, in Unit 7, we're going to look at conservation laws. With the first one that we're going to revisit is conservation of energy. So you may have done a lab in which you rolled the ball down an incline way back in the work energy power unit. And your teacher or someone may have said, hey, do a percent difference calculation, right? And you get in there bigger numbers, right? You're getting like a 30% difference or a 20% difference. Well, because when you roll a ball down an incline in that unit, you're focusing on a sliding object, but a ball doesn't slide, a ball rolls. So now this is why we're calling it conservation of energy revisited, right? Because now we're going to treat that ball as a rolling object and not as a sliding object, okay? So way back in Unit 4, right? We talked about a kinetic energy. More specifically, that kinetic energy is what we call translational kinetic energy. And so that's our K equals 1/2 mv squared. So what I'm going to do now, or what we're going to do is put a little sub t there, right? So translational, again, means linear. Now, but when objects roll, in addition to having that linear aspect, they're going to have that rotational aspect. And so now objects that rotate are going to possess a rotational kinetic energy, or K sub r. Okay, the equation for rotational kinetic energy, right? So K sub r. Well, if we look at our translational kinetic energy equation, well, what's the rotational equivalent of mass? Well, it's moment of inertia, right? What's the rotational equivalent of speed? Well, it's angular speed, right? And so our kinetic energy equation is 1/2 I omega squared. Okay, but again, that rolling without slipping allows you to substitute anywhere for V or omega. You can substitute in V equals R omega, right? Because this is our translational speed, or translational or linear velocity or linear speed. Okay, so I can manipulate the equation to substitute V there if I want to, right? Or I can substitute omega by solving that equation for omega. Now, what we can do is we can rewrite that total mechanical energy equation. So E, right, our mechanical energy is going to be equal to K translational plus K rotational. So it's like our total kinetic energy plus our potentials. So UG plus US. So our total kinetic, or our total mechanical energy. So, our total potential energy. But again, conservation of energy does not change. It tells us that the energy before equals the energy after, or you may see it written as delta E equals 0, right? But you can then write this equation for E both times and just simply cancel out what you have, what you don't have, right? So if an object is sliding, you can cancel out, wrong one. If I have a sliding object, I would cancel out the rotational kinetic energy, right? If I don't have a spring involved, I can cancel out the US. Right, I'm just going to try to whittle it down to give me just what I have in that scenario. Okay, so you can come up with a general equation for the speed of an object rolling down an incline, and it's going to have m and v. But what happens is you use all of your rotational, you use your translational energies to kind of get to that one equation. All right, so let's see how this is in action. So we're going to use our same diagram as before, okay? But we're going to change up the problem. Now we have a 1.3 kilogram block tied to a string that is wrapped around the rim of a pulley that has a radius of 0.072 meters with a mass of 0.31 kilograms. It is a disk, right? So if it's a disk, 1/2 mr squared is our rotational kinetic, our moment of inertia. The block is released. How fast is the block moving after it has fallen through a height of 0.5 meters, right? And so this is 0.5 meters, okay? So because we have, this disk is in play, now we have to use the rotating part of the disk plus also the falling part of the block, right? And so I can say my energy before equals my energy after. Okay, well, I'm not going to write out the whole equation because that would take up a good chunk of this video. But before anything is in motion, the only energy that it possesses is that block, right? And so that's going to be the potential energy of the block, okay? And that's going to equal, well, here's our H equals 0. So after, once it hits the ground, it no longer has potential energy, but it has kinetic energy translationally. Plus, we also have the rotating object, the rotating pulley. So I have the translational kinetic energy of the block and the rotational kinetic energy of the pulley. Okay, so now I'm just going to, now really, this is where physics ends, right? Now I'm just going to do a lot of algebra. Right? I'm going to change the color to do the algebra. So I have MGH. Now, don't confuse your M's, right? So little m is going to be our block, big M is going to be our pulley. So we have the kinetic energy of the block plus the kinetic energy of the pulley. Okay, but here's our I for the pulley, right? Then we're going to say omega is V over R because linearly it's going to move the same with the same speed as the block falls. So I'm going to substitute that in there and watch what happens to our equation. So it looks like we got a lot of stuff. We got mixed, rotating, and linear, but watch what happens with our equation. So MGH is still here, right? I haven't touched that. 1/2 MV squared plus 1/2 my I, so 1/2, let me do that in a different color so it stands out a little bit. So I have 1/2 M, big M, R squared, okay? And then multiplied by V over R. Okay, and that's going to be squared. So once I keep doing my algebra, this is going to be V squared over R squared. All right, and that's going to be 1/2 big M R squared. That's 1/2 plus, and I'm kind of working backwards. Okay, now notice here some things cancel out. That R cancels that R. This V and this V are the same. I have a 1/4. So if I multiply everything by 4, I can get rid of I can get rid of all the fractions, right? So I'd have 4mgh equals 2mv squared plus big M v squared, okay? Again, these v's are the same, so I can factor that out. So v squared 2 little m times plus big M, 4mgh. And I would just say V equals the square root of 4mgh divided by 2m plus big M. Okay, so now I can plug in numbers. So we say V equals the square root of 4 times 1.3. We'll use 10 to be simple, times 0.5, divided by 2 times 1.3 plus our pulley 0.31. Okay, and now we do this and it gives us a speed, right, of 2.96 meters per second. So that is our linear speed as we hit the ground. Now, maybe they'll ask you then, how fast is the pulley rotating? Well, you have your omega, you have your V now, or you're looking for omega, you have your V, and you have your R. So we would just simply do 2.96 divided by 0.072, and that would give us an angular velocity of 41.1 radians per second, right? Don't know what they would ask, but that's, right, that could be, if it's a free response question, that could be a second question. Okay, so here we went back and we revisited Unit 4. Now we're going to look at the third of the 3 conservation laws, which is angular momentum.